This will be the concluding lecture on the two-dimensional crystallography, and in this lecture we will introduce what is called as the International Tables for Crystallography volume A. There are several volumes of international tables, and we are going to specifically focus on volume A, and we will give a brief introduction. Later on the international tables will come back again for three-dimensional crystallography as well. So, starting with this, let us look at in fact these tables can be somewhat cryptic and may look daunting, but with all the material that we have already learned, I think you will find that the international tables can be decoded quite easily. So, what we are going to do? We are going to take a few, very few plane groups and try to understand what the international tables are telling us. So, starting with the plane group P M. So, out here you will notice that the left top corner of the table is the plane group P M, and what are the other things it is telling me? Obviously, we have already explained any plane group which starts with the letter P means it is based on a primitive unit cell, and what kind of a two-dimensional crystal system it belongs to? Well, it belongs to the rectangular crystal system, and therefore, it is a primitive rectangular lattice. On that lattice, we will have the other symmetry elements. One will notice that below P M, this number 3 is written. This is nothing but just a sequence of plane groups. So, these plane groups have been arranged in a certain order, and this is number 3rd in the sequence. If you are wondering what are the first two in this, the first one is P 1 plane group and the second one is P 2 plane group, and I thought that we should just look directly at this number 3 plane group, which is P M. One will also notice another label for this plane group. So, P M out here, this is the short notation, and this one is what is called as the long notation, and it becomes particularly useful if we use certain non-standard configuration of symmetry. And as I had already explained, but to repeat, in this long notation you have 4 symbols. The first one is P or C. So, P is primitive, C is centered. The second one typically would contain the highest symbol for the highest rotation axis. So, if there is a 6-fold and a 3-fold together, one would typically put a 6-fold rotational symmetry here. Third in the sequence is the symmetry plane, which could be glide or mirror, the one that is perpendicular to the A axis. And the last, the 4th symbol is the symmetry plane again, glide or mirror, which is at an angle alpha with respect to the A axis. So, this is just a repetition of what I have already stated in the earlier lecture, and you can see that this notation can be constructed by these set of rules, this particular long notation. So, stuff on the top, there is still this is left, this is mirror, or basically this represents what is the point group. So, this is the point group M. Now, bold lines in this diagram represent mirrors. So, these are all mirrors. Now, sometimes this can be little confusing, because there is very little difference between the bold lines and the lines which are not bold. So, these vertical lines are not bold. So, the mirror lines are, or the mirror planes are horizontal. So, this represents all the symmetry that is present, this particular diagram. The second diagram here is without any symmetry elements, but basically these motifs have been put. So, if this is a right handed motif, this is a left handed motif and so on, and this diagram only tells us how these motifs get moved around in the presence of translation symmetry and other symmetry elements like mirrors, glides and rotation axes. Now, coming to this, so you can see that you can also see now from this diagram that there are clearly two motifs per unit cell. Also, you would notice that one is a right handed, other is a left handed, which is inside the cell. But all of these motifs could be replaced by, let us say, a single atom, which may not have, which may be achiral, which means when it gets reflected, it may not change chirality. So, one can replace all of these motifs with a single atom, or it could be replaced with a bunch of atoms, and those, let us say, some molecule which may get repeated as a result of symmetry. Now, this content here, origin on M, it is basically telling me that origin has been put on the mirror plane. Now, it can be considered as, generally what we like to do is one wants to put the highest symmetry at the corners of the unit cell. In this case, the highest symmetry is reflection symmetry, and therefore, if I consider lattice points at the corners, then the mirror plane, the lattice points are falling on the mirror planes. Now, where is the origin? I should also point out this, that this, as we have already been considering this as the origin in our earlier lectures also, that this is the origin and this is the unit cell axis A bar and this is the unit cell axis B bar. So, that kind of clears this and how the motifs get distributed. Now, let us consider this item asymmetric unit, and it says 0 less than equal to x less than equal to half, 0 less than equal to y less than equal to 1. That is, x will vary between 0 and half, y will vary between 0 and 1. So, where x axis corresponds with the a vector and the y axis corresponds with the b translation vector. So, this basically defines an area. And clearly, if I were to look at the diagram, let us say this diagram with the motifs, this area, so remember this is my x or a and this is y or b, this being the origin. This basically defines area which is half of the area of the unit cell. Interesting to note that there are two, let us say, atoms. If I had put single atoms, 2 atoms per unit cell. So, the area of this, the area, if I were to write what is the area of this asymmetric unit, it is basically 1 divided by the number of atoms if I had put single atoms, or if I put any arbitrary motif, then it would have been 2 motifs per unit cell. So, it is a half of the total area of the unit cell. Now, what is this asymmetric unit? Well, basically all the stuff, all the objects that are present inside this asymmetric unit, all the motif elements, or let us say I had put a single atom only, then there will be only one atom in this. When operated on by translation symmetry, by reflection symmetry, by glide symmetry, etc., will generate the entire pattern. So, we just need to define one small unit and let the symmetry operations work on that unit, and we generate the entire pattern. So, basically in this unit, whatever atoms I put, those atoms will get operated by the symmetry elements and generate the entire pattern. Then we come to symmetry operations. What are these symmetry operations? Basically all the symmetry operations that are present. This one of course is the identity operator, which will always be present. and this one out here is the reflection symmetry or a mirror plane, and it is also telling me. So, this is the mirror and this is telling me its location, and its location is 0 comma y, basically means x is equal to 0, y is any value, which basically is representing this line, the horizontal line 0 comma y, and since all the patterns are infinite in nature, this also is represented by the same coordinates 0 comma y. Now, we come to this last part in this particular section, generators selected. These are the minimum symmetry operators, which when operated on all the motifs or on the asymmetric unit, this is the minimum number you require to generate the entire pattern. So, this one is of course, this is representing to this symmetry operation. So, this is operation number 1. These are the translations. So, one is along A, other is along B. So, T 1 comma 0 is along A, T 0 comma 1 is along B, and this is the second symmetry operation, which is number 2 listed here, which is the mirror operations. So, with this minimum set, I can generate the entire plane group, you may say. Now, this is just one part of the table. This is in fact one half of that page of the table. The second half looks something like this, till the plane group P M. This is rather an interesting and an important part of the table. It talks about something called as multiplicity, Wyckoff letter, site symmetry, and below that is the table. This column out here is multiplicity. This column, the third column out here is site symmetry, and the middle column in which letters A, B and C are written, this is simply called as the Wyckoff letter. And out here are the other columns are having some coordinates. Now, what is this? Let us just first go back to this. Let us say the motif I put here, which is not lying on any symmetry element, is called a general position, and it will have coordinates x comma y. So, it is not lying on any, here the only symmetry that is present is mirror. It is not lying on the mirror plane, but it is lying in a general position where there is no symmetry element present. That is called a general position. Now, how does that, what is so important about the general position? That if let us say if an atom, let us just focus on a single atom. If a single atom is lying on a general position and let the symmetry operate on that atom, it starts out with the coordinates x comma y, the reflection operation. So, if this is the coordinates x comma y, the coordinate here clearly would be x bar comma y, that is x bar representing minus x. So, it will be minus x comma y because of the reflection. Now, how many atoms we generated? If I put a single atom at x comma y, I generated 2 atoms. If I had put a molecule, I would have generated 2 molecules. So, basically this is what multiplicity is. How many motifs got generated in a single unit cell and what are their coordinates. So, here it is written x comma y, x bar comma y. Now, you may say that the coordinate of this is not x bar comma y. So, basically we are considering these two, we can do that, we are considering only these 2 atoms as our, which are part of this unit cell, and the other pairs like this are part of the adjacent unit cells. Or we can equally well write that I can add a translation of 1 unit. So, it would become We are now going to talk about fractional coordinates. We are not going to talk in terms of A and B. If there is a translation of A, we say it is a translation of 1 unit, translation of B, it is a translation of 1 unit and so on. So, the coordinate of this would be x bar plus 1 comma y. I could write that, but this and this are equivalent. So, I can actually live with this set of coordinate system. So, here for example, side symmetry is 1 in this case that we discussed, which essentially means no symmetry. That means, it is not lying on a symmetry operator, or I should actually say it is not lying on a point symmetry operator. If I consider this, these are what are called as spatial positions. Which lie on a symmetry element. Here this M is showing that it is lying on a mirror plane. Essentially, it has basically taken out this 1 M1 and it is lying on one of the M's that is there in the middle, which is basically means it the mirror plane which is perpendicular to the x axis. So, how does that matter? Well, actually I could go to this diagram and try to understand this. Suppose I put a motif here, the reflection operation reflects it, or I put an atom, the atom gets reflected. But instead of doing this, if I put this atom directly on the mirror plane, when the mirror operates on it, the single atom gets self coincides with itself. So, it does not produce another copy of that atom, but of course, the translation would produce an atom here, and then similarly translation along B will make an atom here and will make an atom here. So, now how many, if this is a single atom, how many atoms are there? Well, half from here, half from this one and 0 from the other two, which means there is a total of 1 atom per unit cell. If it is a molecule which has a, it has to have that same symmetry, or an object, it has to have the same symmetry, it has to have a reflection symmetry. If it falls on it, then it will be that motif, that object or that molecule. So, again 1 object or 1 molecule per unit cell. So, in that case, so I get 1, let me call this as object per cell in this case. Now, if I look at this, this is, it says multiplicity is 1. So, that is what it is. There is only one entity in the unit cell when I put that motif on the mirror plane. Now, there are, you can see there are 2 mirror planes. This mirror plane is on the coordinate 0 comma y, or I should say, if I look at it, it is 0 comma y, and out here the middle mirror is half comma y, the third one is part of the other unit cell, or it is called equivalent to 0 comma y. So, I have 2 such spatial positions, one at half comma y, other at 0 comma y, and both have the same multiplicity. Now, this Wyckoff letter, so actually these Wyckoff letters run up like this. The first one, rather the bottom one in the table is assigned the letter B, letter A, the next row from the bottom is assigned B, the letter B, and the third row, there are only 3 rows here, is assigned the letter C. So, these are just a sequence of letters A, B and C. So, we can actually refer to them as Wyckoff positions A, B, C, and we need not specify a lot. So, these tables tend to be very concise in that way. So, one can define a structure by saying that this atom lies on this Wyckoff position A in this particular plane group, and that completely defines the crystal. Now, there are other stuff like this which I will not do right now, like what is this reflection condition. We need to have a reasonable idea of what is structure factor, which we will try to understand when we come to X-ray diffraction part of the course. And this one also we will not go into any detail right now. I will look at it briefly, but this probably be a little bit beyond the scope of this course. Now, coming to another plane group. This time I have focused on the plane group CM. So, I have the letter C, which says it is a centered. In fact, as soon as I see C centered, it has to be rectangular, because that is the only plane group in two dimensional lattices which will have a center lattice point. And of course, the same thing, so it is rectangular, centered rectangular. This is the long form of the plane group. I hope you understand that now. This is my point group, so no problems should be there. Again, it says the origin lies on the mirror plane, and that again is the highest symmetry, and that is what we are doing in this. Now, here if you look at it, let us look at this asymmetric unit. Here let us see how many motifs are there. So, there is 1, I can count all the ones which are inside, 2, 3 and 4. So, there are 4 motifs or a single atom. So, 4 atoms or 4 molecules per unit cell, and therefore, I expect that the area of the asymmetric unit must be. So, area here should be 1/4 of the total area of the cell. So, 1/4 of the total area, and if you look at this, this actually clearly defines that it is 1/4. So, x varies over 0.5, y varies over 0.5, that means the area that we are defining is this one, which is clearly 1/4 of the unit cell. Again the same this thing, that let the symmetry operations operate on this asymmetric unit which contains various motifs, and you will generate the entire pattern. These are as before, but a little bit more involved here. These are the symmetry operations. Now, let us look at this. It is referring to with respect to 0, which is the lattice point at the corner, and it is. So, this is for 0, this one is half, which is the lattice point at the center of the cell. So, for 0, if I look at the operations, of course, identity operation will always be there, and then I have the mirror plane as before in the case of the plane group PM. Here, this is the centering translation. And this is also a lattice translation, which takes fractional units T half, half. Essentially, this is nothing but the translations from the corner to the center. Then we look at what symmetry is this. It says B first of all 1/4, y. Now, where is this 1/4, y? Well, this is 1/4 of A. So, this is 1/4 and y all along the y axis, the horizontal axis. So, essentially this is a glide, this is a glide plane and this is mirror. Now, there is this letter B. So, I could have written G as a glide, but it is telling me more by not writing G as a glide, but writing B. Basically, this is saying that this is a B glide. Now, what does this mean? This B represents the direction of the glide translation. So, direction of glide translation, which is along the B axis. So, that hopefully becomes clear. This is again the minimum generators, minimum symmetry generators to populate the entire pattern. Identity, these are the translations, and now it is not just along A and B, like this is A, this is B, but this is the centering translation, which is basically A by 2 plus B by 2, and this represents the symmetry number 2, which basically is this, which is basically nothing but mirror on 0, comma y. So, that I think I have covered everything in this first part. If I look at the second part, again there are special positions and general positions. Now, this is special position. This special position has a multiplicity of 4, but I see only 2 coordinates here, but there should be 4 coordinates. So, the 2 coordinates, but we have to read this table with reference to what is given here. It basically says to add to these 2 coordinates 0 comma 0 in one case, that will give me 2 coordinates, in another case add half comma half. Adding 0 comma 0 give me the same coordinates x comma y, x bar comma y. My third coordinate would be now add half. So, it will be x plus half comma y plus half, and the fourth one is add half comma half to x bar and comma y. So, x bar plus half and y plus half. So, this way I have the 4 coordinates, and you can verify that when you look at the plane group diagram. So, this is a general position. This one is a special position when your motif is lying on the mirror plane, and here it is 0 comma y, and then you can add half comma half to this, and you will get the second one 0 comma no half comma y plus half, and you can see that there is a multiplicity of 2. So, that takes care of this plane group. Let us go to the third one, P4 mm. Now, I am sure, and this is the point group corresponding to that, and this is basically a primitive square. Origin at 4 mm, always we are trying to put the origin at the highest symmetry. Asymmetric unit is a little more complicated, 0 less than equal to x. So, x is varying between 0 and half, y is varying between 0 and half, and x is less than or equal to y. So, these are the constraints put. So, we have to find out what is that area. But before we do this, you look at this, you put a motif here, the mirror reflects. So, this is right handed, this is left handed, 4-fold takes this pair and rotates through 90 degrees, forming a total of 8 motifs per unit cell. So, I expect that the area of this will be 1/8 of the total area. So, that is the asymmetric unit. Now, where is that? 1/8 clearly means that any one of these triangles will do, but it is referring to one specific triangle. It does not really matter, it could have been another triangle. It is essentially referring to this, or I can define it in this. So, all it is telling me is that if I have only one motif in this asymmetric unit, the rest of the symmetry operations, the rotation axis and the translation axis will create the whole pattern. This one is a set of symmetry operations. Now, number of symmetry operations have gone up. I have now mirror planes and glide planes and many other things that are going on, but here as you can see, we are only written down the mirrors. I have the 2 folds and the 4 folds. This is the minimum set of generators, identity, then the translations along A, B and C, then the symmetry. This one number 2 is this one, number 3 is I am referring to this one, and number 4 is represented by this. This is the minimum that is required. So, I think this is clear. Coming to this one, now there is a much bigger table of positions, and there are, of course, this has multiplicity of 1 when it is sitting on a 4 mm side symmetry, it has multiplicity of 2 sitting on a 2 mm point symmetry, and here it is sitting with 3 more special positions which have multiplicity of 4, and this one is the 8th one, which is general position. Rest all are special positions, and I think it is fairly simple and you can work it out yourself. This is kind of an assignment for you to work this table out. And the last one I have taken from the hexagonal based plane group P31M that we did in the last lecture, and P31M we have already seen that we have these mirror planes along the edges and the mirror plane along the short diagonal, and then we have the glide planes. If I put one motif here, the reflection will take it here, and this pair can be rotated around by the threefold, giving me basically total of 6 motifs per unit cell. Again, origin is kept at the highest possible symmetry. Again, always the origin remains here. This is the A axis, this is the B axis, and the asymmetric unit has steadily become more complex. Somehow we have to define an area which will be 1/6, because 6 motifs per unit cell, 1/6 of the total area. Now, you can go through it, but the table also gives us the vertices of this area. So, if I just look at the vertices, we can quickly see this. So, I have the vertex here at the origin itself 0, 0, half would take me here, 2/3, 1/3 will take me on this threefold rotational symmetry, and then I have half, which is the center of the cell. So, if I join this, then the asymmetric unit is out here. In this asymmetric unit, whatever motifs are present, they will get replicated by the symmetry operations. So, hopefully this part is fairly clear, and if I want to know, is this area really 1/6 of the total area? So, think about it. We have, if I look at it, I have these equilateral triangles. There is triangle 1, this is second one, this is third one, this is fourth one, fifth one, sixth one, seventh one, eighth one. So, each triangle, each equilateral triangle has essentially 1/8 times A total, plus if I now look at this part, this is occupying 1/3 of the area of a single triangle. So, I will have 1/3, and a single triangle area is 1/8 into A total, and you can do this simple arithmetic and one will get 1/6 of the A total area. These are the positions, this is general, these are special, and one thing I did not mention, maybe I can come back here for a bit. You see, all the special positions are lying either on a mirror plane or a rotation axis, and even if you come, let us say, to this particular plane group CM, the special position is lying on a mirror plane, while it also has glide planes, but glide plane is not a special position. So, you can understand it like this. Let us say that I have a one atom lying out here. The glide will simply shift it through the glide translation to this position. It will become, but anyway, a single atom, and it has to have the reflection symmetry present in it, and this mirror will reflect that single atom out here. And so, what is the multiplicity for this? The multiplicity for this is 4. So, it has the same multiplicity as the general position, even if the atom was not lying on a glide plane. Therefore, glide planes which have translation, glide translations are not special positions. And that is about it. The rest we will come back, we will revisit these tables when we talk about the 3-dimensional space groups and when we also come to the X-ray diffraction part of the course. But this marks the end of our discussion on the 2-dimensional point groups and plane groups or 2-dimensional crystallography, and the next lecture we will start discussing three dimensional crystallography, where because of the presence of the third axis, there are going to be lot more point groups and space groups. In the three dimensional case, there are going to be 32 point groups and 230 space groups. Of course, we are not going to go through all of them. The reason I went through two dimensional in more detail is that then understanding three dimensions is a lot easier. So, with this I end the lecture. Thank you.